Welcome to the group exhibit Hydrogen Fuel Cells and Batteries at the Hanover Fair 2017. We are here at the Technical Forum and my name is Muriel Burkas. Unfortunately, we're already coming to our very last presentation of the Technical Forum 2017. I hope you enjoyed it so far and you are very much looking forward to the last presentation. I would like to also give a warm welcome to our guests watching the presentation online through our live streaming. Please join for some coffee and some refreshments. And I hope you look forward to the last presentation as much as I do. It will be regarding solid oxide electrolyzer stack development for oxygen production by in-situ resource utilization on Mars. Please welcome with me on stage Program Manager of Ceramatec, Jessica Elwell.
Thank you for the introduction. As she said, I'll be discussing our NASA-funded program to produce a small-scale electrolysis unit to do CO2 electrolysis on Mars for oxygen production. A little bit of a program overview. Most of the technical discussion will be focused on the stack itself, but the Mars Oxygen In-situ Resource Utilization Experiment, or as we shortened it to MOXIE, is one of 7 major experiments that were chosen to fly aboard the $2.1 billion Mars 2020 rover, which is a Curiosity-class rover. The purpose of the experiment is to demonstrate the use of Mars atmosphere, which is 96% CO2, for the production of oxygen to prove out both breathable oxygen and propellant production on Mars. The system we developed is about a 0.5% scale system. Just for the testing, this was due to, which we'll go through, a lot of the constraints on the program. The full system will be a 200x scale up, and that will be for the propellant production. Oh, I should mention, and our team that specifically worked on the solid oxide electrolysis, or as NASA went against the norm of calling it SOEC and called it SOXE, or SOXE, our team was Ceramatec, Plance, who did our interconnect development and production, the Jet Propulsion Laboratory, and the Massachusetts Institute of Technology. A little bit about the mission itself. We are expected to launch in July or August of 2020. It will then take about 7.5 months to reach Mars, where we will go through entry, descent, and landing using a system similar to what they did for the Curiosity rover. Once there, the prime mission is 1 Mars year, which is about 2 Earth years, and we will operate multiple times throughout that 2-year period to operate at different seasons, different times of day, that type of thing. Of the 7 experiments, MOXIE is the only experiment geared towards preparing for a manned mission to Mars. So this is a diagram of the overall MOXIE system, which has a scroll pump used to feed the CO2 into the stack, the SOXE stack itself in the center, and then the oxygen and the CO and CO2 product sides are put through some measurement systems that will confirm purity and production rates. And then for this experiment, since it's so small, it will just exhaust to the atmosphere. There's no collection system for this. So SOEC on Mars, I had to put this diagram in. Our web developer made it, and I laughed so hard when he put this up. This is the final stack design. When we started the proposal, we were thinking of all the different challenges we were going to face with this, and we thought for sure the hardest one is going to be dry CO2 electrolysis. There's no water. I mean, they say there's water, but not for this experiment, and there's no hydrogen available. So we're doing multiple operational cycles, and we have no way to flow hydrogen into it and do any sort of recovery if we see degradation. But we learned quickly as the program began there were many challenges to the program. It was not just what the feed gas was. We had Pressure differentials. Mars atmosphere is about 7 millibar. We had product purity, which we knew that we'd given consideration to, but didn't fully understand what was involved in what's required for launch, entry, descent, and landing. The stack is made of brittle materials, and we're going to put it on the top of a rocket, launch it, and then crash it into a planet. So there's some considerations there we didn't make for our stationary applications here on Earth. We also had limitations since we are housed in the rover itself on power, on mass, and on volume. And we had some interesting considerations regarding operational cycling. In our heritage design, you turn them on and you run them for an extended period of time. In this one, we have 90 minutes to heat up. We run for 120 minutes, and then we turn it off. So the operational cycles are pretty extreme. We also have to take into account temperature considerations. The stack itself will get as low as whatever Mars ambient is, which can be as low as negative 40 degrees Celsius. So our thermal cycles go all the way from negative 40 C on Mars up to the 800 degrees C operating temperature. Another really interesting constraint for us was on Earth we run in a hot box, so it's full heating all around, very even heating. The packaging designed by the Jet Propulsion Laboratory has 2 end heaters on the unit itself. So top and bottom heating, electrical current gets applied, heated up in 90 minutes. With this, it required some considerations for material changes. With this pretty extensive thermal cycling and operational cycling, we made a switch from our heritage ferritic design for the interconnect and incorporated Plance's CFY interconnects, which have a closer thermal expansion match to our electrolyte itself. So this allows us to get a hermetic seal with our sealing technology we developed, and allows us to go through the different thermal cycling. We also had to make considerations to make our material set more coking resistant. So we had some material changes there, and we had to prove out that we were not having any anode delamination in electrolysis mode. Just a little overview. I feel like at a fuel cell conference, people probably know what this is all about. But our material set is a Plance CFY interconnect. Again, we had a joint operation with them to do the design, the production. Took 2 cycles of design to work out everything for the structural considerations. The anode's a multi-layer construction. Our electrolytes are heritage Scandia stabilized zirconia, another multi-layer construction for the cathode, and then the other side of the interconnect. The targets that were set by NASA for this program have kind of changed throughout the program. It's an experiment, so they weren't 100%. The rest of the system wasn't fully defined when we started developing this stack. So now where we stand, we are expected to complete 20 full operational cycles. They're planning 10 on Earth, 10 on Mars. And then for extensibility, as you probably know if you follow the Curiosity at all, it's still going. They're still doing experiments up there. So we want to be able to operate as long as this rover is moving around and still has power. So we did proof tests where we have one going on right now that will end at 60 cycles. Again, we have the 99.6 oxygen purity. For the proof testing at JPL, we had to be able to cycle to negative 65 degrees Celsius. The packaging has some pretty interesting considerations so to help the stack and the installation make it through the forces it sees for launch, entry, descent, and landing. So they put a pretty significant force on the stack itself with the compression rig they designed. And we, like I said, we have to be able to withstand shock and vibe. So I'm going to go through a little bit of the testing we did. A lot of this, the actual test was done at the Jet Propulsion Laboratory, and then the stack was returned to us for operational cycling. This is a picture of how they instrumented the stack. The stack is inside of this box. This is the SOEC packaging, and then the SOEC stack is within. That has all of the heaters and everything incorporated in. What they did is they have what they call proto-flight, which is what they expect to see on the mission itself, and then they put their safety level of +3. So they did that test. I'll go through the operational results after. We did the thermal cycling, as I mentioned. To do this, because this is an experiment, a lot of these were just done by demonstration. We did a lot of modeling that supported the results that we ended up getting in the demonstration testing. But this stack that was tested, it was first vibed. It went through vibrational testing, and then it did 40 cycles to -40°C, 3 cycles to -55 degrees Celsius, and 1 cycle to -65. We also did testing on the different components of the stack themselves. We had a new braze joint development that we did with Planche, and we needed to prove out this type of braze because it had never flown on a flight mission before. This one's my favorite. So here we took the stack and its packaging, and we mounted it on a beam. Here you can see the beam, and then we shot a projectile at the beam. So this is about a 4-inch diameter projectile. They did this on 3 axes. So they mounted the system to the beam, hit it with a projectile, took it off, put it on in a different direction, hit it again. Apparently it's very loud. I got to see the video, but. So after each of these tests, we did operational cycling at Ceramatec. And in these, we saw no significant change in either oxygen purity or in performance. You'll see our performance metrics on your left are in area-specific resistance. This was the requested way to present this by JPL. So we do see some cycle-to-cycle changes, but they're very small, and they are not any greater than what we see just from operational cycling itself. So very successful. This is a bit of an interesting eye chart. We have taken 3 stacks to 21 cycles and met all of our mission requirements as far as end-of-life oxygen production rates and end-of-life purity. But what we're doing right now is the 60 cycle test, and as of yesterday we were on operational cycle 56, and we are still going through, still hitting our purity target. We're actually, I believe, at 99.8%, and we're still making our production rate target of 6 grams per hour at 55 gram per hour feed rate. That's controlled by us. We go for the target. We want to operate safely. We want to make it to 60 cycles. So we're not doing anything. I was going to say we're not doing anything interesting, but I don't agree with that. We aren't doing anything to put the stack in known danger. We've done a lot of modeling looking at Nernst potentials and where the voltage is going to favor carbon formation over oxygen formation, or over CO formation. You'll notice a pretty broad range on this one of the ASRs, and what that is due to is this testing is done at varying flow rates, varying temperatures, and varying currents. So each cycle has something different that we're testing on it, much like it would be on Mars, where we don't expect the pump to feed the same thing every time the pump is turned on. So a bit of a breakdown of the last 2 years of work. As I mentioned, I mentioned in yesterday's talk, sorry, not today's. We have completed flight qualification at Ceramatec, meaning that all of the stacks that are being built are to aerospace flight quality standards. And with that, we have built 21 consecutive stacks that are performing at 1.6 ohm centimeter squared ASR on dry CO2 with greater than 93.9's purity. As I mentioned, the structural stability testing, we did our compression testing and took the stack to 10 kilonewtons load and then retested it after that load was applied, no change. Then we tried to find the fail point on the stack because nothing broke at 10 kilonewtons, so we went to 25 kilonewtons, still no change, so we tried to break one, and it took 62.2 kilonewtons, which on the footprint of a stack, just to give you an idea, stack's about that big, it's the equivalent of placing an African elephant on top of it, it turns out, when you do the conversion. As I mentioned, shock and vibe testing with no major changes, and our cryocycling as well. So where we are now is, as I mentioned, we're in the flight build process. We're building 11 stacks. One will be hand-selected to go to Mars. And we are doing a lot of this operational modeling so that we can feed NASA the data that when they get the feedback from the rover a day after, or the day that the stack is cycled, they can make a consideration for the next operational cycle so they know to keep it in a safe operating mode. So we're not stressing the stack any more than we need to. On the Ceramatec side, we've done a really great amount of work in the last 2 years on this program and some other programs that we have going on right now. And we want to scale this up to have a commercial offering of solid oxide electrolysis stacks. So we are in the process of forming Oxeon Energy, which right now is a part of Ceramatec, but our goal is to really move from Ceramatec's traditional focus on research and move into, through our prototyping and into manufacturing. So that is all I have for presenting. I want to thank everybody for their time. I should mention MIT for managing the program, the Jet Propulsion Laboratory for the technical management, and of course NASA for the funding. And if you have any questions that we can't get to after this, I'm in Hall 27, booth 38-2. It's right over there.
Thank you very much, Jessica. Are there any questions from the audience?
Hello.
Hello.
I was wondering, how many cells do you have in the stack?
8.
And
sorry.
Another question, what is the most crucial thing to get at such good mechanical stability as you have?
So it is a 10-cell stack. The interesting thing in the design is the mid plate. They wanted to make a capability to operate each stack independently. So you'll see there's 3 sets of bus bars. So it's technically 2 5-cell stacks. The plan is to operate it all together, but they wanted a little bit of redundancy in the case something would go wrong with a cell on the stack. As far as the considerations for the mechanical integrity, we did a lot of modeling and a lot of flow design, and it was a very specific and one I won't show design that we came up with Plancé that optimizes not only contact area but overall structural stability on the electrolyte.
Are there any further questions right now? So it sounds very successful so far.
So it's fantastic, yes.
Great.
I think so.
And you have another 3 years almost?
So what they will do now is we're delivering stacks. We've given test stacks to the Jet Propulsion Laboratory for the integrated systems testing. So they'll do that for a little bit, and then they'll hand off to the Mars 2020 team. I believe it's in 2018. And then the full integration into the Mars rover itself will occur, and then it goes to launch. So we're done this year, but we'll still support the packaging activities and the test activities at JPL and the operational modeling.
And then you want to take your product further for commercialization?
Yes,
right.
correct.
Thank you very much for this very interesting last presentation of the Technical Forum.
Thank you.
If you have further questions, it's just behind the Technical Forum. So go have a look at their booth 38 and talk to her about this great project. Thank you very much.
Thank you.
We are at the end of the Technical Forum 2017 at the Hanover Fair. It was a pleasure to have you here. Thank you very much for your questions, for your interest. I hope we will see you again next year at the Hanover Fair at the group exhibit Hydrogen Fuel Cells and Batteries. If you've missed any presentations this week, please go to our website. You can find all the presentations, no matter if Technical Forum or Public Forum, on the website, and you can watch it again. Today will be a special night for our exhibitors at the Bavarian Hall. I hope we will see all of you there. And otherwise, thank you for your attention and see you next year. Thank you very much.